It's my pleasure again to provide a summary of what the Phoenix program can do for you. And I will talk a little bit about the combination of pharmacokinetic continuous response with pharmacodynamic that can be also non-continuous. Then what's the challenge that we have? With clinical trials that we are dealing with both continuous response, like like regular pharmacokinetic data, and also continuous pharmacodynamic data, disease response model. But the reality is also that we involve also the use of non-continuous response, like multi-level data, for example, disease state 0, 1 to 3, and count data, like number of cardiac events accumulated from observation to observation, and also time to event data. And the combination of all these types of response is really challenging, and the Phoenix NLME software has been designed in such a way that without losing flexibility, you can really take advantage of very useful interface that allow you to build very complicated models with minimal of work. When you are using Phoenix NLME, you have three possibilities. You have three modes that you can use. The first mode is called built-in library, like you have in non-MEMS, that you can use a pre-specified model, like pharmacokinetic model, pharmacodynamic model, and other kinds of models. But most of the time, the real models that you need cannot be found only in the built-in libraries, and you have to shift to the next level, which is the graphical mode. With the graphical mode, you can define processes like zero order, first order, or mixed order processes. And you can build very complicated models using the interface, the graphical interface. Automatically, whatever model you use with the graphical interface, any model is translated into a code. And then, if you finish with graphical mode and you still have some feature that cannot be defined either with the built-in libraries or the graphical mode, you can shift to the textual mode. And you can easily shift from one mode to another mode. When you go from built-in to graphical mode, the built-in will create the graphical mode corresponding to the built-in library. Then you can refine the graphical mode. And at the end, when you need to add, for example, some initial conditions that cannot be done with the graphical mode, you can ask the program to shift to textual mode. And whatever you define with the graphical mode is automatically translated into the textual mode, and then you can do the change that you need to get your final model. Then it's something that is very, very useful, that it's really unique to the Phoenix environment. There's no other program that can do that. Then, of course, if you are talking about statistics, a very, very well-known program is a SAS program that can handle easily categorical response of all kinds. Then what's special about the Phoenix is that not only it can handle statistical, very complicated statistical kind of response like discrete data, but it can easily combine the pharmacokinetic data with non-continuous kind of response. What SAS cannot really do, especially when you have a complex design with respect to dose and input. Now I'm going to explain you how we can map your model thinking strategy. For example, when you have data, the question is that what are you going to do first? What are you going to do second? Is there a mapping between the optimal thinking process and also the Phoenix NLME environment that basically can do whatever you think you should do, can you do it with the Phoenix environment? Then let's just show, let me launch the screen share. And I'm going to show you first the pharmacokinetic part. See? Okay. Then here's the model, and I'm going to show you the model building steps. You have the data. In the data, you can see you have the patient, you have the time, you have the PK data, and you have, in that case, you have different categories. level, like disease state. And you have a complicated model where you have implicit absorption. And that's basically the same drug, the same amount, the 300 units of drug can be absorbed by two different processes. A fraction will be absorbed directly, and a fraction will be absorbed late, at later stage. Then the first thing that you need to do, and that you can do very easily with Phoenix, is just look at the data and say, okay, I want to get some information about the main parameter I'm going to use in the model. The main parameter are volume and clearance, and also absorption. And you do an NCA. In the NCA, very easy to use. You sort by ID, time with time, and concentration. And also you tell the program, this is the kind of dosing that you have. At this point, the only thing that you need is just to get some information about initial estimate that you can use for volume and clearance. Ka, which is the absorption rate, can also be a first estimate by just multiply the lambda z, which is the terminal elimination rate, by a factor of 10. It will give you some information about the case. Then you do the NCA, and then you do on the volume and the clearance and lambda z, you do descriptive statistics, and all this is done within the Phoenix environment. And then you get, okay, I got a clearance of about 8, a lambda 0.14, which means that I can use 1.4 as initial Ka, and also a volume of 60. So you say, okay, then I have the first information for modeling purpose. Then now I'm shift to the first model, which is the one compartment model. And you can see that if you are using the one compartment model, I'm going to take advantage of the NCA that I perform, and I'm going to use the 160 and 8, which are the average value that I could get from the NCA. Ka, I multiply roughly lambda z by 10, and I just round up to 1. Then I run the 1C Ka with this initial estimate, and I'm getting already output. I get a lot of generated output that I can look. And these are called diagnostic output. For example, you can look at the conditional residual, and you can see the blue line should be really around 0 and flat. And you can see that it's moving a little bit. And you have another one, conditional residual versus average concentration. Then you say, okay, then maybe I should try the two compartment model and then use a statistical tool that allow me to differentiate between 2 and 1. When you go to the two compartment model, the cookbook that I designed tells you, take the final parameter that you got for the volume and clearance, and just use roughly the same value for V2 as V, where V2 is the volume of the peripheral compartment, and CL2, which is the intercompartment clearance between the central and the peripheral compartment, and just run the model again. Then you run that model again, and then the question is that, okay, is 1 or 2 better? The Phoenix environment allows you to make statistical comparisons called the model comparer, where in the setup you say, okay, I want to compare 1 and 2, and then I want to run that model, and I'm going to get the p-value. If the p-value is less than 0.001, it means that the two compartment model is better than the 1, at least statistically, and you are going to choose the compartment. You can see here that it's almost 0, which means that I'm going to use the two compartments. Now, suppose here that we have prior information that tells me that in fact the dosing input is a little bit more complex than just one absorption site. And in that case, it's known that we have basically more than one absorption site. In that case, 2 absorption sites, but we don't have the built-in library. You can make a copy of this model, the 2C, and then you can shift to graphical. When you shift to graphical, for example, here I already shift to graphical, what's happening is that your model is created. Sorry. When you shift to graphical, let me see if I can do it here because I really cannot see. Change to text will be lost. Continue. I'm just going to show you if I have the graphical here. If I'm in the graphical mode, like you can see, this is the graphical mode. I can add compartment. In that case, I add an additional absorption compartment, and I can tell the program that the dose is going to enter the second compartment with a delay, which is called T-lag. And only a fraction of the drug is going to enter to basically through that path. I log it except it's a function that we have in NLME that is bounded between 0 and 1. And if I have 1 minus that fraction, it means that the remaining fraction, which is I log it excess, for example, I log it effect is 0.3, then 1 minus I log it effect will be 0.7. And 0.7, 70% of the work will enter into that part, 30% into that part. Again, the fraction is the parameters will be estimated by the program. And here, you can run that model. You can run that model, and then you are going to get the results. And you can, again, you can look at the results, you can look at the final parameter, you can also look at all the plots. And then at the end, you are going to see that you get basically very good results. You can see that before we had a blue line that was not really flat, and now it's really flat. Remember the rules. The blue line should be around 0 and flat. The red line should be about plus 0.7 and minus 0.7. And roughly 90% of the data should be between minus 2 and 2. These visual diagnostics allow you to get a good feeling about how good we did the fit. Okay, then we get good results for the PK, but now we need to shift to basically the PD, that is categorical. Again, we have different categories, I think 0, 1, 2, 3. And here's the categorical response. The question is, the problem with categories is that it's more difficult to have an assessment about how we should define a model, and also how to find good initial estimate for this kind of model. We are talking about categories. When we are talking about continuous response, we have a model, and we don't even think about in terms of probability, because we don't really need to do it. Once we are talking about categorical response, we need to define a model in terms of probability. We have 0, 1, 2, 3, we have 4 categories, and we need to define a model for the probability. Then the probability here, what you can see, if we do an histogram and we look at the different doses, you can see that the probability to be in category 3 increases with concentration. Basically, when I increase the dose, I increase the concentration, and so is an increase in the probability to get category 3. The way to define probabilities when we have different categories is to define probability to be in level 3, the probability to be in level 3 or 2, and the probability to be in level 3 or 2 or 1. These are called cumulative probability. The rules that we need to be respected are that the probability must be between 0 and 1, and also the probability to be in 3 or 2 must be larger than the probability to be in level 3. The probability to be in level 3 or 2 or 1 must be larger than the probability to be in level 3 or 2. And this can be done by using the following trick. The I log it function, it's a function that will always define the value between 0 and 1. Then if I have I log it of AC plus B, I know that it's between 0 and 1. Now the probability to be between 3, the probability to get the level 3 or 2 must be larger than the probability to be in the level 3. How we can define a function that will ensure that it will be larger than the probability in level 3, it's very easy. You just take the same formula, I log it AC plus B, and you add D when you force D to be larger than 0. Finally, we need to define the probability to be in level 3 or 2 or 1. We can use the same formula like we defined before, and we add the parameter E that must be larger than 0. Now, look here at what is in red. This is what is important. The program now will make your life easier. Easy. The program is going only to ask you what is in red. It's going to ask you how many levels you have, which is 4 levels. You are going first to tell, you know what? I have a response that is categorical. And I'm going to show you this in 1 minute. I have a response that is categorical. The transformation to get the rest is called the log it transformation, because log it of I log it cancel I log it, and then if you do a log it and the I log it, you get what is in red. Then the program is going to ask you how many responses. You are going to tell 4 responses. Then 3 windows will show up, and you need to define AC, the 3 terms that are in red, starting with the larger one, which is AC plus B plus D plus E. Then the next window, AC plus B plus D, and the last window, AC plus B, where C is the concentration, which is the link between categories and exposure. Then let me show you now how we do this in practice. Then again, I define the model in terms of cumulative probability, and now I'm going to show you how the interface will make my life easier. I'm just trying to, here. Okay. Okay, good. I'm there. Then you can take the same model that you had before, which is the PK model, and what you need to add is to tell the program, I have an observation that is categorical. And when you do that, automatically you can see that the program opens a window and is asking you what is the link. And I told you that because I'm using ilogit, in order to get the red part, I need to do a logit of the ilogit. By the way, you can use also probit and log and cl log. Then the next step is say, okay, first you need to define a slope of 0 because all is in red should be written in the intercept window. Now you see only one window, but we have 4 outcomes. And you click here and you say, okay, I have 4 outcomes. And then you see 3 windows that open. And let me delete that. And let me show you basically what was done. Then again, I did it. I defined a categorical response. I put a slope of 0. I told the program that I'm using the logit transformation with 4 levels. The 3 windows show up. And then here, I just put AC plus B plus D plus E, AC plus B plus D, AC plus B. I'm not going to explain you how to find the initial estimate because this would take basically a full webinar. But I can tell you the constraint that you can put for some of the parameters. As I explained you, D and E must be positive. You can click on parameters and you click on fix effect. And then you can add program basically. Let me show you here. Hopefully you can see here. You can see that I put an initial of 1 and I can put a boundary of 0 for D and for E. And this, when I'm doing that, I know that D and E always will be positive. And then I can run the program, and then you are done. And when you get the results, you are going to get the result here. And the important result is the theta, which gives you an estimate for a final estimate for the categorical base model parameter A, B, D, and E. And you know that D and E must be positive, and you can see that with positive. In the patch that is going to be released very soon, you can copy that model to the workflow and just accept all the final estimate that has been generated by the program and just shift from the simple mode, which is a fit, to a visual check. And when you do that, you can also add a table, but I'm not doing that. When you do that, the program is going to take the same data set and is going to now simulate from the final distribution that has been estimated by the program. And the program is going to create many replicates of the same trial and is going to give you the PK response and also the categories that are now simulated. When you do that, you can then compare the observed categories that has been given as input, which is here. For example, here, when I'm taking the dosing of 10, 100, 200, and 300, I know that the average category was 2, then 2.5, 2.7, and 2.9. And you can take the simulated categories, because this is what I'm interested in. You can take the simulated categories at each dosing and just ask the program, do I get something similar to 2, 2.5, 2.7, and 2.9? And this is done here. And you can see here that if I'm talking about the categories, I'm just going to start here, sort here. And you can see here that I'm getting 2, 2.5, 2.7, and 2.9. H1 instead of 2.9, then you get some feeling that you get by simulation from the final model that has the population characteristic that was generated using optimization. You can see that I'm getting very similar average categories value at each of the dosing. And this gives you a good feeling that we did a good job. Then if I summarize, if I want to summarize what I did so far, there are two different steps. First, I feed the model to the PK data, and I told you that you can use the built-in, the graphical, and eventually the text model. It was not needed here. And then the second step was to create a model for the category. And again, the interface, the graphical interface allows you to do this very easily. And then I can fit the full model to the data, and I can get the final, basically, estimate for my full model. And at the end, I can challenge my results by providing visual predictive checks and to see if I can simulate categories that are very similar to the one that I observed. And now I will turn to Andre to basically go to the next step. Question and answer.
Thank you, sir.
Andre?
Yes, I'm here. Let's go to Q&A. We have a couple questions that did come through. Question number 1. Can NLME, Phoenix NLME, give you upfront error messages before running the model? And if so, and if it does it work in all 3 modes?
Yeah, I think it's a very, very good question. It's something very special about NLME, especially if you have a model, for example, that is built-in or graphical. Sometimes you can use what is called pre-compilation, which means that before you even run the model, the program is going to give you some error if you made error. The best pre-compiler is the one that basically is used when you shift to the textual mode. Then you can do your model in graphical, and before you run it, you can just shift to textual. You don't lose nothing because you can always come back from textual to graphical. And if you have error, the program is going to show you the error interactively. If, for example, you type some code and you do an error, the program automatically is showing in red that you made an error, and also to show you where's the error. And it's something that is very special because all the other programs you need first to write your code, and when you are done, and sometimes the code can be 2 or 3 or 5 pages, and when you are done, you click the run, and then you are going to get the error. And that's something very special about NLME, is that there's a pre-compiler that allows you, before you run your model, interactively to show you potential error that you made.
Okay, great. One last question we have in here. They understand that predefined models for categorical responses are available, but how do you define the more complicated models for the non-continuous responses, and is it as flexible as non-mem?
Yeah, I think it's really as flexible, even more flexible than non-mem, because on one hand, you have predefined likelihoods like that we have, for example, for count, time to event, and interval data. Now, if your likelihood is really complicated, then you have a statement that is called the log likelihood statement. That is similar to what you have in non-mem. If you want to use the log likelihood statement, you can basically write the code for your log likelihood itself. And it can be as complicated as you want. And then when you do that, then basically you run the same model, and you don't have the constraint that it is either multi-level, count, data, or time to event. It is whatever it is, and you can always define any kind of likelihood that it's continuous or non-continuous or mixed using the LL statement.
Okay, and actually we just had this last one come through. What optimization algorithms can you use for the combined PK and categorical responses?
If you have continuous and categorical response, you have different engines that you can use. The one that you should use first is called the Laplacian. And the reason to use the Laplacian is because you need to really integrate very complex models because they are categorical, especially if they are combined continuous and categorical. You can also use the naive pool that will assume that you don't have random effects. And you can use also the QRPEM, which is a quasi-random parametric expectation maximization algorithm that works with both continuous and categorical response. And I think that it's a huge advantage over some other software because you can use different algorithms. I think that you can use the same algorithm with non-MEM, but not with monoliths that do not have naive pool neither QRPEM. But yes, the SEM algorithm is also a very good algorithm. And you have really full flexibility, and sometimes the program is going to work well with one algorithm, and sometimes with another one. You know, this is the real world, the real world of modeling, but sometimes it's very complicated.